Okay. Hi, everyone. So today we're very happy to have Benoit Collins from Kyoto University telling us about some interesting mathematics, random matrix theory, and beyond. Thank you so much.
Yeah, okay, so well, thanks for the introduction, and it's a pleasure to be here virtually. So yeah, it's going to be actually pretty informal and perhaps not maybe less than 1 hour given the late time here in Kyoto. So I the request by Nima was about some things related to the cone embedding problem. But since I don't have myself some very like recent and relevant works in this direction, I chose to speak about something which is also infinite-dimensional, but which is free probability actually. So and applications to quantum information theory. So free probability and applications to quantum information theory. So and hopefully it will be a chance for you to I mean, I'm assuming no knowledge in free probability theory, so I will just try to say a couple of words about free probability theory. So the way I'm going to say that is that so this is that's actually originally that's a branch of operator algebra. Operator algebra. Operator algebra is the study of all the in general, roughly speaking, is the study of bounded operators on a Hilbert space. I mean, it's more, but you know, it all gravitates around that. But very interestingly, so this was maybe in the 80s when it was founded by Voiculescu. And but very interestingly, actually, it has evolved into a branch of probability, maybe an extension of probability, and in particular, random matrix theory, in particular, RMT, which stands for random matrix theory. Random matrix. So, but and so that's where I entered the field more or less. But I will try to speak also a bit about the abstract part of it. So first of all, what was, of course, like I say, it's a branch of operator algebra, but there is already the word probability in it. So what did Voiculescu had in mind? So the motivation was something which was called the Cadison isomorphism problem. Isomorphism problem. Maybe I will skip some definitions, but so let's take what we're going to use throughout is FM, which is the free group on M generators, which I could call maybe U1 ... UM. So so these are group elements which generate a group, and there is no non-trivial relation. like U1, U2 is not equal to U2, U1. And as soon as you create a word, the only way to have it be zero is, to have some UI inverse, which cancel and so on and so forth. So with the UI inverse and the associativity rules, nothing else. So that's the free group on on M generators. And Caddison's problem is now if I say that let L of Fm, let L of Fm be the von Neumann algebra of the free groups. Whenever I have a group, I can send them. I can create an operator algebra with it. So typically we have the C-star algebras and the von Neumann algebra. So maybe not give the definitions, but you could think of it as maybe some version, non-quantity version of an L infinity space somehow. So bounded measurable functions, non-quantity version. And the question is this von Neumann algebra isomorphic to the von Neumann algebra of another free group when n is not equal to m? That's Caddison's isomorphism problem. And
Can I ask a quick question?
Sure.
So the von Neumann algebra will depend on a choice of measure, right?
So yeah, actually, well, let me let me give the definition. The definition is what you have is you could create the L2 space of the group. You see, where each element is an orthogonal norm one vector, and then what you can do is you can the group Fm acts by shift on the left on L2. So it's a unitary operator. You could think of it as some kind of permutation. Okay. So which means that actually Fm I can embed it in the unitaries of L2 of Fm. And then what you do is you take all the linear combination of this and you take the weak closure. So maybe this is the weak closure. And it turns out that you don't really need actually a measure behind. But you're right, actually. When I say L infinity, there is a measure behind. But actually, what is known, even when you look at classical L infinity spaces, is that the L infinity space will be the same as long as the two measures are absolutely continuous with respect to each other. So
correct. Yes. Good.
That's the kind of phenomena that we have. But actually, the fact that there is a measure behind it indeed is important. So maybe I'm going to let me mention that, like it's going to be somehow statements in a random order, but this von Neumann algebra L of Fm has a unique threshold state tau, which just satisfies that tau of with respect to disembedding, tau of a group element, okay, is just going to be 1 if and only if it's the identity element and 0 else. And I can extend this by linearity and continuity, and this is and that turns out to be trivial. So let me get back quickly to this just for motivation. It's clear, of course, that if n and m are not the same, the groups are not isomorphic because they don't have the same number of generators. So if you look at the star algebras, at the algebra of non-commuting polynomials, if you want, in Fm and Fm, you think of each element as a variable, if you want. Then a similar reasoning proves that that we don't have isomorphism. Now, if you look at something which is called the reduced C-star algebra, where you, instead of taking this weak closure, you take an operator norm closure, which comes from the BH structure here, then they are not isomorphic as well. And here it's a topological argument, some kind of K-theoretic argument. But it turns out that when you try to work at the level of measure, so at the level of fundamental algebras, people didn't know if they are not isomorphic. I mean, it's not isomorphic to many other group fundamental algebras. Here, if you have a group which is called amenable, then it's not isomorphic. I mean, there are many things which are known, but within the realm of free groups, which somehow are probably the most non-competitive groups, in one's imagination, at least, whether we could have some classification of these non-competitive spaces, these non-competitive L infinity there, was an important question by Caddison, and that question was actually the motivation for Voiculescu to kickstart free probability theory. He hoped actually that the fact that these fundamental algebras have a unique tracial state would allow him to think of them as a non-commutative probability space. So,
can I ask a quick question?
Yes.
So L of Fm, is it a type 2-1 non-hyperfinite factor for all n larger than or equal to 2?
That's right. That's exactly right. So the unique tracial property is equivalent to being here, since it's finite, it's equivalent to being indeed a 2-1 finite factor indeed. And so a 2-1 factor is an object that is in principle it's very natural to look at as a non-commutative probability space. So namely, every element X in maybe L of Fm is a non-commutative random variable. And maybe you could have something like tau of X is its, maybe you could say its non-commutative expectation. So Voiculescu said, let's try to have a probabilistic approach to that problem. And very interestingly, he did not solve the Caddison isomorphism problem, which is still open 45 years, 43 or so years later. However, it doesn't mean that it was a bad idea. Actually, it was a wonderful idea, and it led to lots of very incredible developments. So I think I always hesitate somehow to give a definition because I'm not sure it's really insightful. Maybe I will give it, but let me rather explain what it's about. So,
can I ask a quick question?
Of course, go ahead.
So I understand that if you have a finite trace, in this case, it's a nice non-commutative probability space. But
Right.
in general, if you just have a von Neumann algebra and some state, what would mathematicians call that a non-commutative probability space? What is missing? I mean, the tracial propertiness, why does that matter so much?
Right. So to have a non-commutative probability space in general, what you want is you want a pair A and tau, where A is maybe you want some operator algebra. So it could be, if you want a star algebra, at the very least, you want a star algebra at least. But it could be a C-star algebra. Maybe it's better if you have a C-star algebra or a von Neumann algebra. And then tau, what you want for sure is that tau of 1 be 1, because you want that the expectation of the constants, random variable, be 1, that the one random variable be 1. And then you also want positivity. You want linearity, of course. You want linearity. And you want some positivity. You want positivity is something like this. A star is positive. So this is what you want at any cost. And that is actually even well defined in a star algebra. So at the level of so without project. So when if you add C star of von Neumann, you have some kind of continuity, which you want. Maybe here you want something like well, continuity here. Maybe you want normal, something like that, to have some kind of maybe dominated convergence or something like that. But that's actually what one has. And by the way, non-commutative probability has been actually a very active area of I would say pure mathematics. It is still, but it was really flourishing in the maybe 70s, 80s. Something it was also called quantum probability theory. And in a sense, Voiculescu did, I mean, looked at a particular case of non-commutative probability theory. Now, what really matters somehow, if you take the probabilistic point of view, let me just do a probability for 1 second. And in probability, let's say that you have, maybe let's say that you have X, let X and Y be two random variables. So what it means mathematically, it means that X belongs to a probability space, omega F P, and Y belongs. So here this belongs is a bit strange, right? But I will maybe specify what I mean. So what we have is that's a probability space, okay? So probability space is a set of events, and then that's a sigma algebra, and then that's a probability measure which is measurable with respect to sigma algebra, and then you repeat again. And here so you see when you say belong, actually what we have is that X goes from omega to R, for example, and this is measurable. That's basically what it means, to be a random variable. And then you have two random variables which live in principle, they are defined on two different spaces, and you would like to be able to consider the pair XY. And there is in principle no really obvious way of doing so. Even though intuitively, what you could just say is let's take them randomly, right? Let's take them independent. And that's I mean, I don't want to make any categorical statement because I've not delved into that, but so how to consider them jointly? So which means like in a same space. And one canonical way of doing so is to look at the product, omega times omega tilde, and then the sigma algebra will be the tensor sigma algebra, and then the probability will be the tensor of probabilities. So that's a very common. You see, if I have two variables in classical probability, say, well, okay, let's take two independent couples. But when you say let's take two independent copies, actually there is lots of math which is going on. Like there is lots of measure theory and all that, and you just don't say that. But you don't say that because because Borel, Lebesgue, Fubini, all these people have done, and Mark Kolmogorov, all these people have done the work for us basically. And Voiculescu try to see. So here what we have is we have independence. So here the answer is independence. And Voiculescu try to look for a non-commutative version of that. So there was already a version of that, which was the tensor independence. So in, maybe I will say like this. So in the non-commutative world, there was already tensor independence. And so the definition of free independence is completely different. You see, tensor independence is the variables might live in a non-commuting space, but they commute pairwise. So there is still, so maybe we could say it's maybe a commutativity survives. Commutativity survives. And so Voiculescu wanted to get rid of that. I mean, it's not that he wanted to get rid of that. Like he had one case where there was no commutativity, and he wanted it to fit there, so it could clearly not fit in such a context. So that's how he invented freeness, and the definition is that.
Sorry, can I ask you a question, Benoit?
Of course.
So if you have non-commutative tensor product, then commutativity survives. But if you survival of commutativity, does that imply tensor product?
Well, that's not completely clear actually, and I think that this part is actually very closely related to the
Embedded. Yeah.
Exactly.
Yeah. Okay. So that part is open. I see.
And that part is really subtle actually. Yeah. Yeah.
Thank you.
But people actually were not aware of all these problems when this tensor independence was created actually. And all these problems don't actually arise when everything is finite dimensional. So this like infinite dimensionality creates some major problems here. So the definition, I will write definition. If we have maybe some unital subalgebras of a non-commutative probability space. So these are, these are unital subalgebras. So you take a bunch of them and they are free. They are free if and only if I have that tau of A1, A L is 0 as soon as what? As A1 belongs to AI1, A2 belongs to AI2, and so on and so forth, with I1 not I2, I2 not I3, IL minus 1 not IL, and tau of AI are all 0. So it tells you, I mean, it's not completely clear, but if you think a bit algebraically, what it tells you is that if I know tau on all the AIs, then I know it on the algebra generated by the AIs, which is more or less what you wanted here, when you create a pair. You want to be able to say what is the expression of x, y, and x, you know. And here the rule was that expression of x, y is expression of x, expression of y, basically. And you want to be able to do this. And it looks like, you know, you have just done part of it, but with linear algebra. You figured I should you have done the whole job. So just take it as a definition. I've just given a definition because, you know, I chose to do so. But the definition is not very enlightening. I mean, it kind of makes sense maybe if you look at the free group in the first place. But probably what we should say, what I think it's legitimate to say that this is a calculus. This is a non-commutative calculus. So in other words, like if I have two variables which are two algebras which are free, then I am able to understand something like the behavior of the sum or something which involves two free things. Say that. So I'm able to do some calculus thanks to this this rule. And
So can I ask you a question?
of course,
Is there a way of repackaging this condition in terms of some sort of a Q-Millen generating function that helps
yes.
understand it?
Yes. So this has been done. So this has been done by Voiculescu for single variables. So he has explained how if I take one variable in A1, one variable in A2, how I can deduce the moments of A1 plus A2 or A1 times A2 out of those of A1, those of A2. So yes, so there is some version of the Fourier transform, which are called the R and the S transforms. And then Speicher has done something which is much more systematic, which is the free cumulus. I'm not actually going to talk about that, just because but yes, definitely this has been done.
Thank you.
And right, so what's the relation? So here you see I said that this has become a branch of random matrix theory. And why so? It's because Voiculescu actually, Voiculescu in Voiculescu, maybe I will Voiculescu 98 and then 98, 92, 98. Voiculescu, sorry, my handwriting is just terrible. He proved that random matrices. So maybe I would be a bit more specific. Maybe if I have, if maybe something like A I n is a family indexed by I of n by n matrices. And here, the non-commutative probability space which I'm going to use is the one where I take the normalized trace. So here I'm always going to abbreviate it by small trace. You see, that's a non-commutative probability space. That's a C-star algebra, or that's an algebra. And this quantity here actually satisfies what we said here. The normalized trace of the identity is 1, and the trace of something positive is positive because all the eigenvalues are positive. And so if I take an I tuple, it could even be infinite, of matrices, and I assume that it has a limiting non-commutative distribution, which means here I will maybe again speak informally, orally. Maybe actually, let me just do it. So it means that the trace of A I1 n AIKN, this limit exists. It exists for any non-commuting word. So which is actually slightly weaker than having a distribution in the classical sense, but it's very close. If it's bounded, it's the same, for example. And so then what he showed is that if that, so here you see AI could be anything. They could be constant, random, doesn't matter. And then what he showed is that then so does the pair U and then AIN, where UN is hard distributed on the unitary group and independent from all the AINs. So being independent from the AI is an empty condition if they are deterministic. If they are not, you just take it independent, but in the classical sense, you see, in the sense of this. So in the sense which is deemed obvious by any probabilists or statisticians. And so you see, that's some kind of bootstrap, because if I have a family which has a limiting distribution, then I can enlarge it and it will still have a limiting distribution. And this is the limiting distribution. The limiting distribution is governed by freeness of U and AI. So this part and that part are free. So basically, you see that if U is taken at random, of course, it will not commute typically with the AIs. Well, actually, what Voiculus could say somehow is that it's as bad as it can get typically, in a sense, in the sense of this definition. So it's very interesting because this definition actually really arose. This definition is actually quite natural when you look at free groups, and maybe it's some kind of miracle that it turned out to be the perfect fit for random matrices. And so a little bit more of history there. In random matrix theory, like most random matrix theory before Voiculus school was single matrix random matrix theory. So you just have one model and the dimension goes to infinity. And now suddenly we were able to study like multi-matrix models, which was a big revolution in my opinion. I mean, this is more or less, I was born mathematically a couple of years behind that, but it was very, very exciting to see all the developments. So what I would like to do is just give you, after this brief introduction, give you two applications, actually, to quantum information, as I said, of this. So the first one will be directly related to random matrix theory, and the second one will be infinite dimensional. So two applications, I will probably just mention them, two applications to quantum information theory. So QIT is quantum information theory. So the first one actually somehow works through the random matrix thing. So maybe actually it does not, but it's easier to explain it that way. So what let's look at the following fact, which is, I think, probably known to everybody here, but just in case I will state it. So what we have is we have this term of Choi, okay, which say that if I take a map which goes, let's say, from the K by K matrices to the N by N matrices, which is linear, and I will call it a phi, okay? And now what I will do is I will create a map C phi, which is called the Choi map. The Choi matrix, sorry. And what it is, it's just, maybe I should take some notation here. The elements, the canonical elements here, this is EIJ, this is with row I and column J, and this is just a one there. So this element here. And so what you do is that you just put phi, oh, let me go back to black. So phi of E11 here, and so on and so forth, phi of E1K here, phi of EK1 here, phi of EKK there. And that's this map actually completely. So this map, you can think of it as a map which belongs to MK times MN, okay? So it's a block matrix. Each block is N by N. And this map, of course, completely encodes by linearity the map phi. And what we have is that phi is CP completely positive if and only if C phi as a matrix is positive. And so what we decided to do with Patrick Hayden and Ion Nikita, it was about 10 years ago, is try to see what if C phi was a random matrix. And to be more specific, what we would do is we would say that C phi has the same law, the same distribution as a matrix like this, U, D, U star, where this is a random. So this is diagonal. And this is a random hereditary. But a big one, like in UKN. So like it's a big hereditary, and in this very big space here. Well, it turns out that so we have the following result actually. So I will state it like this: we are going to fix. We'll not do things with complete mathematical rigor because I think it's better to just convey the idea. So we fix K, and but we have N, which is large. That's going to be that's going to be the idea, and we assume that D has a limiting. So D as N goes to infinity, a spectral distribution which tends to mu. So maybe you could think something like this, like it has a histogram of eigenvalues, okay, and the percentage of eigenvalues between here and there, is measured by this integral, and so on and so forth. And then what we proved is the following. We proved that, so I will just write the term and then say what it means. We have that C phi is L positive if and only if well, if and only if is again slightly too strong, but I'm going to state it like that way. If and only if mu free additive convolution K over L has a spectrum whose support is positive. So here I have not told you what this is, and I have to tell this, but perhaps before we should double check together what L positive is. So completely positive, I think that it's okay for everybody, right? So if I have a positive map, is a map which sends a positive element here to there. So the definition looks very nice, but I think it's very unnatural in the non-commutative world. Actually, we don't know how to classify positive maps in most of the cases. But CP, completely positive, it means that you can tensor by anything, it will still remain positive. And it turns out that completely positive is much easier to describe. And actually, there is this beautiful theorem by Choi, which characterizes completely positive maps through their Choi matrix. And there is no such thing for positive maps. So L positive means that if I tensor with the L by L matrix, it will still be positive. But if I tensor by the L plus 1 by L plus 1, it might fail to be positive. And so that's the for definition of L positive. And this is L positive if and only if the support of this here, this is called the free additive convolution. So let me tell you, so probably everybody has noted that this is not an integer. So like what the heck am I talking about? But for now, you see what we have is, it's quite clear what we mean in the classical setup. Mu free convolution, L time. This is the law of maybe like x1 plus xl, where these are IID variables, something like this. So that's and and now likewise, mu free convolution IID of law mu. Likewise, mu free additive convolution L times, this is the law of x1 plus xl. And here this is freely identically independent distributed of law mu. And so that was the question of Nima. This is actually calculated. And so what we have here, you see, is we have a semi-group property. And it is for sure indexed. Sorry. This is indexed by n. Like I can take the free convolution 0 times, which is the delta 0, the Dirac mass at 0, and then 1 time, which is mu, twice, which is mu convolution mu, and so on and so forth. So we have this semi-group. And the shocking fact is that, so maybe I can write it like this. So this is a shocking, sorry, should spell it properly. Shocking fact, which is by Nika and Speicher. The free convolution semi-group extends to 1 plus infinity. So look, for example, if I take a Bernoulli distribution, 1 minus 1 with probability 1/2 each. I can take the convolution twice, 3 times. I cannot take the convolution 1.5 times. This is just simple combinatorics. Because how could you have, if I had 1, how could I have this 1.1 convolution convoluted with itself be equals to mu convoluted 3 times? You just do the combinatorics, it will never work. Well, it turns out that it works for free additive convolution. And so this guy here extends to that. So here maybe I should have said that L is between 1 and K, because actually, as soon as L reaches K, I am automatically property positive. And that can be seen easily from the proof of choice theorem. So here actually we're looking at some quantity which is bigger or equal than 1. And you see, it's very interesting because there exists, so like one example. So one example, one non-trivial example. Trivial example is if I start with a shifted semicircle distribution. So this is a semicircle. So this is a semicircle shifted by A. So here this goes between -2 plus A and 2 plus A. The semicircle is between -2 and 2, and I shift the whole thing by A. When you take the free additive convolution, you actually, so if D has this distribution, it will not be property positive because this is not CP if A is less than 2 absolute value, for example. But it turns out that as soon as A is strictly positive, there exists some L such that the free additive convolution L times has positive support. So this is actually related to a phenomenon which was discovered by Berkovici and Voiculescu. Which is called superconvergence. So you see, what we have in classical probability theory is that if I have a random variable which has a positive expectation, but which could be negative with some probability, then if I take some convolution of it, it will always be negative with some positive probability. It's a probability which will decay exponentially fast. That's large deviation, but it will always be positive. And in free probability theory, this phenomenon never occurs. To be more specific, it never occurs as soon as the spectrum is bounded. So what we have is, you see, we have a phenomenon where the average when I convolve, the average L times will be L times A, and the variance will grow like square root of L. So you expect the vast majority, the central limit theorem, you expect at some point the vast majority to be positive. In classical probability, it's just the vast majority, but you will always have an exponentially smaller amount which will remain negative. In free probability, that's not the case. At some point, you will have 0%, which will be negative. And so free probability, and specifically superconvergence, thus captures in a very interesting and somehow unexpected way the fact that, you know, this L positivity exists in the non-competitive world, whereas it does not in the classical world. And I wanted to I'm not sure I should do the second part because I will be way over time. So so maybe what should I do?
Actually, do you mind saying a few words about this, how this is used in quantum information theory? People like Hayden.
Yes,
Yeah.
right. So okay. Yeah. So maybe I will finish there, and sorry. So I will break my promise and not speak about the second part. I will just say orally what it was going to be. So what's the use of that? The use of that is the interest in quantum information theory is that this could be entanglement detection. So, for example, if I have a map, so if, for example, phi is one from, let's say from mk to mn is one positive, which is positive, okay. Then what happens is that if I apply phi tends to identity L, let's say, which is then going to be a map from mk tends ml to mn tends ml, it will send well, okay, send something like this, some AI tends BI, where these two things are positive, to something which is positive. Okay, because that's a positive map. So this is positive sent to positive, tens identity positive. And these guys are actually called separable. They are a linear combination. They are a convex combination of positive people, of tensor positive. So they are separable. So one positive map, if I tensor by the identity, it sends separable to separable. But if it's not too positive, then you can find a positive sorry, you can find, let's see, you can find x in m k tens m l, which is positive. I put a plus for positive, such that phi tens identity L of x fails to be positive. And then we say that phi detected its entanglements. So that's the use, from my point of view, of maps which are positive but not completely positive. you can detect, so here right, you can detect a map which is which has some two entanglement, and so on and so forth.
But
Um,
sorry, but I think to relate it to the theorem you discussed, you need some sort of a random map so that the Choi matrix is a random matrix, right?
exactly. So then the question, so what is the most famous example? The most famous example is the transpose, which sends A to A transpose. This map is positive, but it's not completely positive. And so it's a very natural way to test entanglement. If I have a positive matrix, if I apply the so-called partial transpose, so this is called the PPT test, positive partial transpose, then the map is then the state is entangled. So what we did, and one of the things which we proved is that actually the typical volume of states which is measured by such random maps is actually which is detected is like these maps typically detect much more than than the PPT criterion. So I mean that's our application. But you're right actually to prove that we need some random techniques. So you see like it detects things typically, but what it detects depends on the map itself.
So the idea would be to pick some sort of a map that corresponds to a random Choi matrix. And you could talk about the probability of detecting entanglement, right?
Yeah. That's
I
right.
see.
Yeah.
I see. Right.
And I will probably stop here because it's quite late. But I so the I also wanted, well, okay, I didn't measure my time well enough. I in the infinite world we have also something which is I will just so application two would have been a violation of regularized minimum output entropy, which is a work which I did with Sang-Yoon Yoon from Seoul National University. And what we have is in infinite dimension, we have some tensor set, some commuting setup actually, in which we have some quantum channels for which the minimum output entropy is violated. So that in finite dimension, this is equivalent to violation of the classical capacity of the additivity of the classical capacity, which would have been very exciting. In infinite dimension, we don't have this because this is infinity minus something, and we cannot say anything about that. But anyway, the problem of additivity of additivity. But the problem of additivity of minimum output entropy was really an important problem in the last 10-20 years in quantum information theory, and the solution was actually given with random matrix theory. And I would say that I mean the optimal solutions available so far, like the solutions which give the best violation, have been obtained with the help of free probability theory. So that's just a teaser for the next time, basically. But yeah.
So sorry, you're saying that the additivity of channel capacity is violated in an extensive way. Using these examples, you could construct examples that violated extensive, because Hastings' example was not extensive violation, right?
Well, it depends what you mean by extensive. But for example, with Hayden and no, with Nikita and Belinsky, we have a violation of log 2 or 1 if you prefer. Depending how you count.
Do you mind writing the reference so that we could look this up? Because this is a topic of interest to us. We spent
Yes. So
Yeah,
this
about
is Nikita. So Belinsky, Collins, Nikita, and we wrote 2 papers together, one in Invenciones and one in CMP. And the one in CMP has the best constants. And the one in Invenciones has the theory basically, but the one in CMP has all the constants. And there is actually some. I mean, in this one there is some quite tough analysis related to these definitions out here. So like there is lots of free probability which is used actually to understand that.
Let's see. Which year is this from?
We
Roughly.
have only 2. The 3 of us only have 2 joint
fine.
papers.
I'll find it. Thank you.
Yeah. I think maybe
Yeah.
2014.
Okay. Thank you so much.
Yeah.
All right.
So okay, so I'll stop here.
Thank you so much. Are there questions? More questions for Benoit? I do have a question. Let me just stand here. So, at least naively, there's this story of Q deformations, right?
Yes.
Which basically, like for Q equals 0, you get free probability theory, and so you get, for example, for GUE ensemble, you get Wigner matrices, and it sort of interpolates between free probability answer and the central limit theorem. I guess I'm asking how much of this story generalizes to I guess what's the RMT side of it? Because the Q deformation, I mostly understand it in terms of Q deform commutation relations. Is there some
Yeah.
sort of an RMT picture behind it?
There is.
The T-star algebra.
So there is a random matrix model for this. I think the cleanest one was established by Speicher. Well, actually, very recently, I think one of my first property of this year with Miyagawa. We touch a bit on that topic. So we describe this model. It has to do with something which you call epsilon freeness. So epsilon freeness is where you have some, like a percentage of the matrix of the elements which are independent and the percentage which are free, something like that. And then you from this you can get a Q freeness actually. So there is a natural way to do that. Initially, Schniadi gave an ad hoc random matrix model, but it was it was not very natural in a sense. But definitely there is some random matrix behind that. Yeah.
Thank you so much. Any last questions? If not, let's thank Benoit again.
Okay. Well,
thank you so very much for this very late talk. Have a good evening.
So see you. Bye.
Bye.